What can I do for you?
It's about question 8 of the online homework. I was having a problem trying to understand the Boolean expression according to the table that was given, the input and output table. I don't know how to do it.
All right, let's take a look at it. I'm going to share my screen with you.
All right.
So, are you looking at
Yes, 2.4, question 8.
2.4? All right, let's scroll down to question 8.
Yes, this one, yeah.
All right, so we're given an IO table. So one of the things to understand about the Boolean expression for an IO table is that we will only write the input states for output that is 1, which means hot wire or true. For example, see the second row? Now, I don't know if mine looks like yours.
Mm-hmm.
Does mine look like yours?
Let me check. So it does look alike.
Okay, because sometimes they vary it. So it's web assigned section 2.4, problem number 8. So we have input variables P, Q, and R, and an output variable S. And that's always the way it is with IO tables. We'll have some inputs, maybe 2 of them, maybe 3 of them. And you could have more, but we never see more because it's just too time consuming. Um, and we care about where the ones are in the output because we want to write the expression that describes the input that give us the hot output, that give us S equals 1. So we're interested in row 2 here. We're interested in row 4, and we're interested in row 6. Does that make sense?
Yep.
All right, I'll stop sharing and let's take a look at this. Under P, it's 1111, which is like true, 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 true. And then O, 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 which is like false, 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 false. And then under Q, it's 1100, 1100. This is the canonical way to set up a 3 input IO table. Then under R, it's 10101010. And the important thing is that there is a 1 in the output column in row 2, and there's a 1 in row 4,
And
and
6.
there's a 1 in row 6. Great. So we only care about these rows because these are the only rows that yielded hot output. So what we want to do is we want to describe the input that yields or produces hot output. In other words, S equals 1. We only care about those rows. Okay?
Mm-hmm.
So remember when we did our do now problem in class
Yeah.
and we played this game where we were looking at the rows that have a true or hot or 1 output, and then we looked at the input and we figured out how to write this input state. So, for example, for row 2, P is true or hot, Q is hot, okay, it's true, and R is cold. But we write what's true. So what's true in this row is that P is true
And
and Q is true
not
and
R.
and not R.
Oh. Oh.
Remember?
Okay. Can
And
I check?
so when we finally write our solution, we're going to OR together
Oh,
those input states. And there are three of them
oh,
that
okay.
yield the hot output. And one of those is P and Q and now R. I won't spoil the fun for you.
So this would be P, not Q, not R.
And we and those together because all of these are happening at the
Mhm.
same time.
Yeah. Okay. 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 Let me check. Okay. Let
And
me.
then this form that we're getting right here is
Mm-hmm.
that famous form called
Boolean.
disjunctive normal form
Um,
because the last operator are these big or operators. So
Okay,
these are
that was the bird I was
disjunctions.
missing.
Does that make sense?
Yeah. Yeah.
Okay, and I'll let you plug this in here, and then you'll write the expression for row six input, and
That
you'll
would
put it
be.
here.
Mm-hmm.
So this is row four input,
Mm-hmm.
and this is row six input. And what that does is it gives us a complete description of the situations, the inputs that give
Mm-hmm.
us the hot output. If this happens, or if this happens, or if this happens to be our input, we get a hot wire out.
All right. That was where that was what I needed. I just
Great.
remembered. So that was the only thing that I had the issue on. So let me continue the homework, and that's all for today for me.
Well, thank you, Karen. Is it Karen or Karen?
Karen.
Karen. My
Yeah.
sister's name is spelled the same way, but we pronounce it Karen because we're Southern. But Karen is
Oh,
uh-huh. But Karen is the usual pronunciation. So I tell you what, if later, if you need like a Saturday or Sunday office hour, you can always email and ask, okay?
yes,
And I will be
definitely.
here. I will be here until 8 tonight.
Today?
Yes, I will
Okay.
sit and wait and see if anybody else pops in.
All right. Because I already started my homework, the online one, and I'm actually done with it. But it's only question 8 that I haven't finished yet. So I was like, let me wait for office hours and then I'll finish question 8. So,
That's so
um,
smart because that way you don't destroy your chances, right? You only get
mhm.
what, three shots at it or something.
Yes.
Well, that's
So,
wonderful. I'm going to pause this now and I will sit and wait and see if anyone else comes.
all right. Thank you, ma'am.
You're so welcome. I realized that I had not set the closed captions on. I just had a student here in the office hour, and we looked at problem number 8 from the WebAssign, section 2.4. I'm going to talk through the solution so that it can be available in closed caption. If you don't need that, you can skip ahead. Maybe someone else will come in. The point with this problem is we want to write the expression that describes the input states that yield the hot output, the one under the output S. I've set up this IO table in canonical form. Under P, we have 1111, 0000. So this corresponds to what we used to do in truth tables when we would write true, 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 false, 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 false. Under Q, of course, we have 1100, 1100, and under R, we have 1010, 1010. In this particular problem, the ones appeared in the output column in row 2, 4, and 6. And the assignment is to describe the Boolean expression. And the Boolean expression, when we read it from the I/O table, turns out to be written in this nice disjunctive normal form. So we worked through the expression for the input in row 2, because that's the first row, when the output variable s equals 1. In row 2, P has the value 1, Q is 1, and R is O. So you can think about P is true and Q is true and R is false. Or you can think about it as P is going to be a hot wire, Q is a hot wire coming in, and R is a cold wire. We always write what is true. To express that P and Q are true and R is false, we write P and Q and not R. We write what's true. If R is false, then not R is true. So this is an input state. P and Q are hot, R is cold. If these wires are input into the circuit associated with this I/O table, the output is a hot wire, and we care only about input that yields a hot output. Row 4 has S equals 1, and the description of the input for row 4 is P and not Q, because Q is O, and not R. Notice that these are ANDed together. We're using AND across the row. But if this first input P and Q and not R happens, or if this second input is what is being input, write that here, or the third input is what's being input here in row 6, I'll let you write the expression for the input for row 6. Then we get hot output. So OR operators go in between the parentheses, and inside the parentheses is a complete description of the input wires. P is hot and Q is hot and R is cold. Then P is hot and Q is cold and R is cold. You would write that one here. And then you would write the correct input state for row 6. This is disjunctive normal form. Why is it called disjunctive normal form? Because the last operator that operates in between these parentheses is the disjunction operator, the OR operator. And it's a normal form because it's universal. You can always get your Boolean expression into a form like this, and it's useful. It's useful because we can read it directly from the I/O table, or given a Boolean expression in disjunctive normal form, it's easy to create the I/O table. All of these values that don't have ones, of course, will have O's. Okay, I'll stop recording and wait and see if anybody else comes into office hours. While I'm waiting for anyone to come into the room, I thought I might show you how to draw the circuit for this I/O table and Boolean expression. To do that, we need to finish writing all the different inputs that gave a hot output. And of course, this one is not P and Q and not R. Again, we're writing not P because that is what is true or hot, because P is false. It's cold. It's an O. So we can fill these expressions in to these parentheses. Each expression inside parentheses is a complete description of an input state that yields a hot output. Of course, this is row 2 input. So let's draw the circuit while we're waiting. We will need 3 input wires, P, Q, and R. Here is P, here is Q, here is R. They are uppercase. And I'm putting a line between them because I know I'm going to need some room. I'm going to just scan these expressions and look and see what I'm going to be building. This expression has a not in front of the R. I'm interested in the not gates, especially right now at this stage, because the not gates have to be built before we build the AND gates. The AND gates are built before the OR gate. The OR gate is going to be last. So there's a not here with the R. Not R appears again, and there's also a not Q. Not R appears again with a not P. I will never need R. I am only going to use not R. So I can run my R through a not gate immediately because I'm ever only going to use not R. I like to build these in order just because it's easier for me if I don't have to think too hard. I have 3 AND gates to build. We can use fan in 3 to an AND gate. What do I mean? I can build one AND gate that will accept the P wire, the Q wire, and the not R wire. And that will be the AND gate for this first expression for this input state. I'll do the same thing for the second input state. A single AND gate can accept the P wire, the not Q wire, the not R wire. And for the third input state, a single AND gate will do. So for this first expression, I need a P wire, a Q wire, and the not R wire. So right off the bat, I'm going to bring a Q wire up close to the P wire. You can bend a wire without a solder dot, but because I'm drawing from the Q wire and this wire that I have drawn up here above it is attached to the Q wire, this wire holds the value that Q holds. I'm going to draw from the not R and bend that, and I'm going to line them all up here. In fact, I'm going to move out of my own way a little bit. I've got the P wire, a Q wire, and a not R wire, and I'm going to put them all through a single AND gate. And there's the output for that. This AND gate is for the input state that I'm labeling with this 1. Now, for expression 2, I do need a P wire, but I need a not Q wire. So I'm going to put my Q through a not gate. I'm going to back this up a little bit so I have room for a not gate. And that's my not Q wire right there. I already have a not R wire here, so I'll just draw from it. And we need a P wire. Now I've got P wire all across here. I can draw from here. I can draw from here. And it's sort of 6 of one, half a dozen of the other, because any way I do it, I'm going to have to cross 2 wires. Oh, unless I bring my P down here and bend it, and then I only cross, well, I still crossed two. Eh, so it doesn't really matter. There's more than one way to draw these. In any case, I've got not Q, I've got P, I've got not R. They are ready to go through an AND gate because they all get ANDed together. That's the AND gate for expression 2, the row 4 input. Finally, we need a not P, and we don't have a not P yet. We do have the not R. Here's the not R. I have a P wire here. I'm going to draw from it and bend it and run it through a not gate so that I have a not P now. There. Finally, we need a Q wire. Okay, we've got Q's here, here. I don't want to draw from there. It's out of my way. But I can also just draw from here, or I can draw from here. Let's see. If I draw my Q wire from here, I'll be crossing 1, 2, probably 3 wires to bend it and put it here out of my way. If I draw from Q here, I'll just be crossing 1 wire. I actually prefer that. So I'm going to bring my Q wire down like that, and I'm going to make these a little bit longer up front here just so that it's clear that they're starting there, and I will run those wires. Let me just double check. I've got not R, I've got not P, and I've got Q. So that's what we need. Not P and Q and not R going through an AND gate. And we do put the name of the AND gate inside the AND gate because sometimes it winds up looking like an OR gate if we don't draw them carefully. The NOT gates, you can put not inside them if you like, but you don't really have to because it's hard to mess up or confuse a NOT gate with an AND gate or an OR gate because the NOT gate has this, nose thingy. Now, the last thing that happens is these ANDed together expressions, this, and this, need to all be ORed together. And again, an OR gate can be fan in 3, so I'll bend this input wire, and this one's a little too long. I kind of like to line things up if I can. There we go. So this is the output wire from the subcircuit that built 1. Here's the output wire from the subcircuit that built 2. And here's the output wire from the subcircuit that built 3. And we're going to put those through an OR gate. And there's our output, which we will label with S. So that's how you can draw a 3-input circuit. P, Q, and R are the inputs all the way to the output S, and have that circuit light up if P and Q and not R, or if P and Q, not Q and not R, or if not P and Q and not R are the inputs. I'll pause this one more time and wait and see if anybody shows up. Well, it occurred to me that I can spend this time and show you something else. You see, what we've done so far is we were given an I/O table. From the I/O table, we wrote the Boolean expression. Once you have the Boolean expression, you should be able to draw the circuit. We also learned in class how to find the Boolean expression if we are given a circuit. You simply read the wires through, and you can review the class notes for that. But let's play the game in another direction. Let me give you the Boolean expression. I'll give a different one. And let's practice building the I/O table for a given Boolean expression. Now, if I ask you to do this game, I'm going to give you a Boolean expression that is in disjunctive normal form. So finding the IO table given a Boolean expression. Boolean expression. So here's another example. Find the IO table for this Boolean expression. I'm going to give you the Boolean expression in disjunctive normal form because this is one of the best applications of that normal form. It makes it easy to build the IO table. Let me show you what I mean. Let's say we have P and Q and R, or P and not Q and R, or not P and Q and not R, or not P and not Q and not R. Okay, we have four input states. Each of these expressions inside the parentheses is a complete description of the inputs that should yield a hot output. So let's just review. Expression 1 says P is hot and Q is hot and R is hot. They're all true. We write what's true. So this will be row 1 of our IO table when all of the inputs are 1, hot, true. The second expression says P is going to be hot, Q will be cold, R will be hot. The third expression says P will be cold, Q will be hot, R will be cold. Do you see what the fourth expression is going to be? What does it tell us about the inputs? They're all going to be cold. And I think we already know that's going to be the 8th row where we have O's across the board for the inputs. So we need only 4 columns because we have 3 inputs and P, Q, and R. So there are 8 different ways that we can mix and match values for these inputs. And then we want to put 1 in the correct rows in the output column. Okay, here we go. Under P, we're going to put 111100. Under Q, 11001100, and under R, 10101010. Okay, I hope you're getting the drift with the canonical setup for an 8-row truth table. That's a truth table, an IO table here, sorry, that has 3 variables for inputs. Now, we will put a 1 in the output column for each of the rows that these input expressions represent. P and Q and R means P is hot and R is hot and Q is hot. All 3 of them are hot. I should have said that in the correct order, but it doesn't matter. We have a 1 here in S, in the column for S. The next row, that we want S to be hot for is when P is hot, Q is cold, R is hot. So here in row 3, P is hot, Q is cold, R is hot. We want a 1 for our output there. The next row that we want S to equal 1 in is P is cold, Q is hot, R is cold. So O, 1, O. O, 1, O. That's row 6. I think we just saw that a minute earlier. And in row 8, O, O, O. We want S equals 1. So put a 1 in each row that is described by these expressions inside parentheses. Of course, O will be the value of S in the other rows because we don't want the circuit to light up unless one of these 4 input states is what is actually input into the circuit. Okay, so now we've played the game in this direction. Go from the Boolean expression to the I/O table. Is it always this easy? No, but here the Boolean expression was in disjunctive normal form, and that's why disjunctive normal form is so popular. It's easy to read the I/O table directly from disjunctive normal form. Thanks for playing. Well, it appears that no one else has questions this evening. So it's 7:56. I'm going to close the office hour and get some dinner. Good night.